All right, now let's practice predicting products of reactions. This is Unit 2, Podcast 2.3. So what we're going to do now is use the type of reaction to predict what the products will be and see how to balance the equation then. So first of all, let's look at what we have. An element that combines with another element. That's got to be a combination reaction. So let's use the charge. Calcium is a 2+, and bromine is a 1-. I don't want to write charges. I just want to use them. So I need 2 bromines for every 1 calcium. And that's already balanced. So that one is done. Piece of cake. Let's look at another one. So if I have manganese carbonate that is heated, that triangle means it's heated, then I suspect we're going to have a decomposition reaction because I have only one reactant. So what happens to carbonates? We form the metal oxide, manganese oxide, and carbon dioxide. That's all there is to it. First tell what type of reaction it is, and then predict the products, and then we look to balance. This one's already balanced. Wow, it's like we've done this before. Okay, I've got a hydroxide and something that starts with hydrogen. So I know this is an acid-base reaction. So water is going to be one of my products. And then the other product is going to be some sort of salt. So let's make water. I'm going to make it this way so I can keep track of that hydroxide. And our salt then is going to be calcium with chlorine. And because calcium's a 2+, then I need 2 chlorines there. And I better have 2 chlorines on the other side. That means I need 2 hydrogens. That gives me 2 hydroxides. And that's great because calcium hydroxide has 2 hydroxides in it. So we've predicted the products and balanced the equation all at the same time. Great. Now let's send an electrical current through lithium chloride. Well, one single reactant means this is decomposition. So I'm going to separate my lithium and my chlorine. But be careful here because chlorine is Brinkelhoff, so we can't just put Li plus Cl. We have to balance the equation for a Brinkelhoff element. There we go. So once you know what type of reaction it is, it's easy to predict the products, most of the time. Now let's talk about this situation. What happens when we have things dissolved in water? Well, then we've got ions to worry about. Complete ionic equations show every ion that exists, and everything that is soluble means it exists as ions in water. So for this reaction, our spectator ions are the ones that show up on both sides of the equation, and they don't change. So here's nitrate, and here's nitrate, sodium, and sodium. Chlorine is on both sides, but on the products, chlorine is bonded together with the silver, so that's not a spectator ion in this case. Net ionic equations then are where we drop the spectator ions and we don't include them. So our net ionic equation for this one is simply that silver ions combined with chloride ions would form silver chloride. Every equation you write, whether it's complete ionic, net ionic, or molecular, needs to be balanced both by the mass and by the net charge to be correct. So let's practice some of these. Whoops. Okay, we need to use the solubility rules to predict the products and write the net ionic equations for these reactions. So I've got my solubility rules handy. If you need to look at yours still, you can look at yours. Let's see what would happen if aluminum were to replace hydrogen. Would we get something soluble or insoluble? So we need to look at the rule for sulfate. Right, here's my sulfate rule. Sulfate salts are all soluble except for 6 exceptions: lead, silver, mercury, barium, strontium, and calcium. So those ones that are exceptions, these would be our precipitates, right? And I don't see aluminum as one of those precipitates. So let's go back to here. And we're going to predict then that aluminum sulfate is aqueous. All right, and then what do we do with our hydrogen? Well, we have 2 hydrogens left. That looks like bubbles of hydrogen gas that will exit the reaction. So since these are soluble and these are soluble, aqueous and aqueous, we can split them apart. Aluminum plus 2 hydrogen ions and a sulfate ion is going to form 2 aluminum 3+ ions and 3 sulfate, which is a 2- ions, and then molecular hydrogen gas. Alright, so we know we can't break apart things that are not aqueous. We're going to leave those together. I can't cancel the hydrogen then, but the sulfate is aqueous here and aqueous here. The only thing is, I can't cancel it if they're not the same. So I should have balanced my equation before I started to do any other mess. I need 3 of these. There, are we balanced? Almost. Balance aluminum. Okay, so I can get rid of sulfate. That's my only spectator ion in this case. So I have 2 aluminums plus 6 hydrogen ions are going to result in 2 aluminum ions and 3 hydrogen molecules. Now let's check charge to make sure this balances. In solid form, elements have a 0 charge, and this has 6+. All right, on the other side, I have 2 3+s for a total of 6+, and this has a 0 charge because now it's an element. So my charge is balanced and my mass is balanced. We're ready to move on then. That one's done. How about another acid-base reaction? I don't think we need solubility rules here because we know we're going to make water and we're going to make some kind of a salt. And it's a chloride salt, so all chlorides are soluble except for silver, mercury, and lead. Let's crisscross our charges. Now I need 2 of these and 2 of these. Alright, let's check the net ionic equation. Complete ionics, let's break apart everything that's aqueous. I get 2 hydrogen ions, 2 chloride ions, 1 barium 2+, and 2 hydroxides. That's my reactants. Water doesn't get to break apart because it is molecular. So there's my hydroxide bound up with the hydrogen. We don't get to cancel those out. And then barium chloride I said would be soluble because it's not one of the exceptions. Let's see, I have 2 chlorides there. Alright, so barium's the same on both sides and the chloride is the same on both sides. And this is pretty typical for an acid-base reaction. For this to neutralize, we would have we would have our hydrogen ions and our hydroxide ions yielding water. And of course, this has to be written in simplest terms, and it is truly a neutralization reaction. There you go, acid-base. Oops. Can we do that? Yeah, we're good to go. Okay, this one looks like we better use solubility because it's double replacement, but it's not an acid-base reaction. So we have sodium and phosphate reacting with barium and chloride. Those are both aqueous, so we'll split all of this apart, but let's see what are we going to make. Barium's going to trade partners and have phosphate now for its partner. So 3 here and a 2 there. And then sodium and chlorine join up, +1 and a -1, that's easy. Now we know that salt is aqueous. The ocean's full of it, right? Full of salt. It's all dissolved. What about phosphates? Let's find that rule. Here's our solubility rules. Phosphate is down here on the bottom. Yeah, carbonates, phosphates, chromates. See right here? It says most are insoluble. The only ones that are soluble are those alkali metals, right? The part of Nakul no so. Alright, so we know if it's not with an alkali metal, then it's going to be solid. So let's come back to our reaction. And yep, barium's not an alkali metal, so that's a precipitate. I don't know how to get rid of this exactly, so I'm just going to pretend it's not there. Let's break apart all of the things that are aqueous. No, let's not. Let's first balance the equation. I need 2 phosphates. And that gives me 6 sodiums. And let's see, 3 bariums gives me 6 chlorines. Alright, so now we've got that to balance, and we'll do a better job then of getting our net ionic equation put together. Get our 2 phosphates, 3 bariums, 2 plus, and 6 chlorides. Then on the other side, we better leave the barium phosphate together because that's a solid. And then sodium and chlorine get to break up. And ions must have charges. If you are writing ions without charges, you are getting the problem wrong. So here's my spectators that get to go bye-bye. And our net ionic equation is something that should make sense, right? Phosphate ions react with barium ions to produce barium phosphate. And that's it. We've balanced the equation and written the net ionic equation.